All right, if the rest of us will go mute, we're ready.
Thank you, Dina. Good evening. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. We are delighted to have Steve Barr as the speaker tonight. Steve has been interested in astronomy since before he could read and looked through encyclopedias to find things that look like astronomical objects. He soon used his father's spotting scope to view the sun, to view the moon, I should say, and look for the planets. Steve was a visual astronomer for many years and went through several telescopes. In 1987, he graduated from Clarion University of Pennsylvania with a degree in computer science and spent 27 years working for Lockheed Martin on aeronautical and space systems before retiring in 2014. Retirement has provided more opportunities to pursue the heavens, and Steve has dabbled a bit in astrophotography and is currently trying to come up to speed on amateur spectroscopy. So, Steve, please proceed with your presentation.
Okay. Good evening to everybody out there. I'm glad that you are tuning in. So, yeah, I don't know that I know everybody personally there, but whoever would like to meet anybody, so any of these events, don't be afraid to say hello. We're going to discuss essentially stars and their characteristics, different types of stars, what they do, some of the things that I've found interesting. And this presentation is actually made for those who just think that, the stars are just points of light. There's so many interesting, fascinating things, I should say, all kinds of stars to look at. And so what we will be discussing is the stellar classifications and characteristics. We'll briefly cover the electromagnetic spectrum, variable stars, multiple star systems, again, just several charts on them, but however, some of my favorite subjects. We're not going to discuss any of the more technical aspects of stars, such as wavelength and frequency, although I'm sure I'm going to mention those words. Spectroscopy, fusion, any of its precipitates. Great deal of emphasis right now in the club on astrophotography, thanks to primarily some great presentations done by people like Joe Pinada and Greg Fogarty, but we're not going to be talking about that. And also, I did eliminate all formulas from this presentation. So we're not going to be talking about anything such as Wien's law, Jean's law, Stefan Boltzmann constant, et cetera, et cetera. You know, why are stars interesting? Well, they're just points of light in the sky if we look at, and pretty much that's what it was like for thousands of years. There are all kinds of different stars that are going to range from blue to red. And from a visual perspective and from a local perspective too, considering our solar system, there are many more things that are interesting, such as the moon, the planets, further away, galaxies, star clusters, nebulas, and I might add, very beautiful things. And actually, probably a whole lot prettier things than just looking at stars. So why do we think that stars are interesting? There are many different personalities and tempers for stars. All variable stars, we have multiple star systems, hot, cold, not quite stars, as I call brown dwarfs, exploding stars, and post-mortem stars, supposedly dead stars, although they still generate a great deal of heat. Just remember one thing, that everything around us, our atmosphere, our homes, the ground around us, they were all made from the core of stars. Just about every element, with the exception of 3, three that I can think of, besides hydrogen and helium, that are only going to be, that are not created in stars. And of course, Dr. Unsoy, you can thank the stars for your morning coffee. I think it was Carl Sagan that said something to the order of, we are children of the universe and made out of recycled star stuff. And that is actually, I think that's a very accurate point. And stars actually may be just as much fun to study as view. I just get a kick out of sitting down and reading a textbook about them. And that's one thing nice about astronomy. It's always been my opinion that you really don't need a telescope even to be an astronomer. All you have to do is have an interest and a desire to learn about heavenly bodies. We'll start off with just some stellar characteristics. And with this chart, what we want to take home more so than anything else, everybody's heard of magnitude and the brightness of objects. Each whole number in the magnitude scale is a factor brighter or dimmer by a factor of 2.512. And 2.512 to the fifth power is 100. As a result of that, a 1 magnitude star is 100 times brighter than a 6 magnitude star. Same applies up to a 11th magnitude star, which is going to, the first magnitude star will be 1,000 times, 10,000 times brighter. And for you astrophotographers that reach out and get 16th magnitude stars, you're 1,000,000 times dimmer than a first magnitude star. And note, I have an M right here. The M would indicate just the visual magnitude. And then we'll go into, well, the apparent magnitude, such as the lowercase m. Rigel is 1.13 magnitude, apparent magnitude, and we have absolute magnitude also. Absolute magnitude is going to classify the star as if it were 32.6 light years away, or 10 parsecs. In that case, Rigel would be almost -8 magnitude. If you want to think about that, in relation to Venus, I'm going to say it's Venus being somewhere around the order of -4. That would make Rigel somewhere around the order of 40 times brighter than Venus. So you could probably just about read the newspaper by it. And another thing that you're going to see occasionally is the bolometric magnitude. It's across the entire electromagnetic spectrum. For instance, Rigel, it's a hot star. As a result of that, some of the light is outside of the visual range in the ultraviolet. So it has a bolometric absolute magnitude of -7.92, just a little bit brighter. And likewise, some of the red dwarfs and red stars are going to be pushed off into the infrared too, outside of the visual range. And some more stellar characteristics. This might be a little bit boring for some people, but however, some of you out there, but like I said, I am trying to develop this as just as a presentation for beginners that want to learn more about stars and some of the things that I had to look up in the process. I'm going to try and save you the trouble of it. If you see the circle with the little dot in the middle of it, that is a unit comparison of stars with the sun equal to one of those. So the mass of sun, if it's 1, Vega is 2.134, and that M is mass, not to be confused with absolute magnitude. Luminosity, for instance, sun's 1, Rigel, information I see says it could be anywhere between 61,000 and 360,000 sun luminosities, which is a great sort of a outrageous range, but many of these calculations that we have with stars have an error of, plus or minus 50%. I'm sure that might change with some of the satellites we have out there now retrieving that data. But however, yeah, you can run into very varying opinions on different things about stars. And radius is another thing denoted by a capital R, with Betelgeuse being 887 sun radiuses. Surface temperature will always be illustrated in degrees Kelvin. Absolute zero is the null point, which is minus 273 degrees below 0 Celsius. Sun's 5,800 K, Sirius is almost 10,000. Another thing you're going to find is proper motion. Proper motion is the rate of angular drift as seen by the observer from Earth in MAS per year. MAS is milliarc seconds, or 1/1000th of a second. Okay, and the star with the greatest proper motion actually is Barnard's star, about 6 light years away from our perspective. And the fastest star actually that's moving in realistic terms would be Arcturus, which is 37 light years away. However, it's 6 times further, so it doesn't appear to move that fast. Okay, and the Harvard classification of stars. Everybody has seen this probably, but I'm going to go over it anyway. OBAFGKM. One of the mnemonics is, O be a fine goat, kick me. O will represent the hottest stars with the temperature decreasing through class M. Second term, and that worked fine. This was all developed at Harvard, obviously, mainly by a lady by the name of Annie Jump Cannon. Okay, and it did have it did start out, I believe, at ABC, etc. But however, they decided to rearrange things without moving the stars out of those little corridors. And as a result, this is what we ended up with. That worked fine in the early 1900s, but however, in the about 1940 or so, things got instrumentation improved, and another factor was added, which is 0 through 9, which 0 indicating the hottest of a class, and the 9 the coolest of the class. The sun is a G2 star. Okay, and stars at times referenced as early to late, with early stars being hotter and late stars being cooler stars. Third term, again, in the 1940s, I think 2Ks, Keller and Keenan, I believe, developed both the second and third terms. And this is to define them further, such as define supergiants as opposed to main sequence or white dwarfs or subdwarfs. The sun is a G2b star, meaning it's on the hot side of the G class, and it's a main sequence star. These are some examples. Elnatak in Orion is an O-type star. They are very rare, as we will see in a subsequent chart. Actually, Elnatak is a double star with an O and a B star, which both of those types of stars are very rare. So that's would be a very rare combination. Of course, we've all heard of Rigel Vega in Lyra, A05. One interesting thing is Vega essentially set the baseline for magnitude 0. And well, Capella, we may look at Capella and see, gee whiz, that's a G3 star. It's pretty close to the sun. No, it isn't. Actually, it's a little bit cooler, but however, that 3 indicates that it is a normal giant, much larger than the sun. And also, I might add, Capella is a double star. Okay, we have Arcturus also, and one of the confusing things is classifying M-type stars, which are the coolest, Betelgeuse and Orion, okay, and Bernard's star. We have a supergiant and a red dwarf, and it just so happens that they're nowhere near in size. You'll be able to see the big difference in them, but however, that's where that third term comes in very handy. And this is something that I would say is a really interesting chart, because it takes all the types of stars from O through M and subdivides them somewhat. But however, if we look at these O3 stars, for instance, the habitable zone in astronomical units, 1,200 astronomical units, these things are red hot. And if we think about this, Neptune is somewhere between, 30 to 32 astronomical units away. You'd have to be 40 times further than that to be able to live around this star. But however, taking that into consideration also, I would not expect to find any type of living, anything living anywhere near this star, for the big reason we only have a lifetime of a couple million years. Since life on this, on the Earth at least, from the first signs of it, which occurred about 3.8 billion years ago, it took about 3 billion years for even simple animal life to develop. So to look for life, I would, my own opinion, and maybe the later F-class stars down, and even the red dwarfs are somewhat arguable. So the electromagnetic spectrum, we only see a very small portion of this spectrum, okay, which extends from gamma rays the whole way through radio waves. For us as humans, it's usually expressed as between 400 to 700 nanometers. Okay, you photographers out there are going to be very familiar with those numbers, because a lot of times you're using your filters or doing narrowband imaging, etc. And we happen to be most sensitive to the green area, right around the O3 area, which is around 550 nanometers. Some animals can see infrared, and some can see ultraviolet too. I think in general, what I can say is it seems like we see what nature and evolution has determined we need to see, and different species need to see different things. So if I would see the way things the way my dog does, I'd probably think they were pretty strange. And likewise, if he would see what I see. Very small portion of the electromagnetic spectrum we are capable of seeing. So just that visible light, and this is pretty much to scale too. So we start out with gamma rays, X-rays, ultraviolet, and then go into infrared, and actually microwaves are in this area before radio waves. Okay, I wasn't going to include this chart about the Hertzsprung-Russell diagram, but then I realized that you're going to run into it so much that I think it's probably a necessary factor if you're going to be studying stars at all. Okay, this was created independently, so they say, and concurrently by Hertzsprung and Russell in the early 20th century. They just established a relationship between spectral class and luminosity, okay, and temperature. And well, temperature is the same, analogous essentially to spectral class. Absolute magnitude on the y-axis, temperature or spectral class on the x-axis. Main sequence stars essentially, if you'd average it out, it's a diagonal from the bottom right to the top left. Okay, and main sequence stars are generally referred to as dwarfs. And also main sequence stars, again, in general, for the most part, they are going to be burning hydrogen rather than helium. And this is the Hertzsprung Russell diagram. Importantly, this is where most stars spend their life, right on the main sequence. You can see the sun is G, and it's just about proportional to a G2 star. What will happen, sometimes you'll see this chart's somewhat similar to this, but however, when stars are done, finish burning hydrogen, and they start burning helium as their main source, they may drift off of this main sequence and go back and forth, and that's what's happened to most of your supergiants. So, and then they'll actually go back and forth, and then such as when the sun, when it starts blowing off all its outer layers, becomes a planetary nebula, and then eventually just nothing but a white dwarf. And I might add, so they say, in the history of the universe, no white dwarf has actually ever cooled down. So it takes trillions of years for that to happen. And this is just a depiction of the life cycle of the sun. First, we start out just as a nebula, and then according to this formula that's called Jean's law, material coalesces, friction and pressure makes it heat up. Eventually, a protostar is formed, and then a what they call a T-Tauri star somewhere from the birth. And after that, we get into our main sequence, and the sun has been in that main sequence for just about 4 billion years. So, but however, if we look at this, it's gradually going to start warming. We might say that, oh, we have 5 billion years before it turns into a red giant, but however, things are going to get mighty hot before then. So maybe we're going to be packing our bags and heading to Alpha Centauri. So, and this is just for a dwarf star. Some of the larger stars follow a similar pattern, except they, instead of just being yellow, they're normally blue, and then they turn into giants also, and eventually, depending upon the mass, will supernova, and that will subsequently result in either a neutron star or a black hole. And if we want to see where we are and just how small we are in this universe, as far as star sizes are concerned, we see Wolf 359. It's a red dwarf. It might be M4, I think, or something like that. But the sun beside it, it looks pretty puny, but however, the sun's pretty small beside Sirius. And then we look down here and look at the difference between Sirius and Aldebaran. And likewise for Aldebaran and Betelgeuse. And right up here to the largest star that we've found so far, which is VY Canis Major. So we are pretty small and insignificant, but however, more important than anything, the sun is very stable also, or else we wouldn't be here. Okay, talked a little bit about viewing stars. Critical factors would be focus, light pollution, seeing and transparency, which I think actually probably focus and light pollution are the big things. The ear optics, we'll talk a little bit about Gauss limit and polar alignment. And one of the things I like to do before I photograph a star, before I go out and point my telescope at, I'd like to get to know a little bit about it. And the reason why I do point at these stars is mainly because I find them very interesting. Okay, might look at the Harvard classification, the distance, the magnitude range, whether or not they're variable, and whether it's something that I want to track over a period of a year, something like that, such as we'll talk about Mira in a little bit. Yeah, my own opinion, if you don't have focus, you're not going to be able to see too much of anything. Okay, with focus, you can visually just get a rough focus is what, well, that's what I normally do. And then I put a Batonov mask on, and I just center the spike in the middle, right in the middle of the star. And as a result, you'll be pretty darn close. And to view stars, you really don't have to be quite so exacting as you do for photography. Some of the other things, of course, light pollution is always a big problem, in particular for us in DAS, because we live near Denver. It's always going to be a factor. Dark sky's always going to be preferred, such as the DAS dark site. Echo Lake, Guanella Pass is one of my favorite places. Rama Reservoir, and just while I'm right here in Parker, just viewing off the back porch, a lot of times I'll just use an Optilong L-Pro light pollution filter to filter out the high pressure sodium lights and whatnot that are shining down from Parker. Seeing is the degradation of an image due to turbulence, okay, in our atmosphere, such as high winds, even unstable jet stream. Adaptive optics can help, but not much use to amateurs. A lot of them are out of reach. Transparency and seeing somewhat confused a lot of times. Transparency is impacted by pollution. It's things that are actually in the air, and light pollution can increase the impacts of transparency. Thus, as a result of having light pollution and it shining through layers of several layers of moisture, you're not going to have very good seeing. So, and actually seeing around here, you'll probably be good to get, it would be amazing. Maybe at some of the dark sites, you might get 2 arc seconds, but normally probably around 3 arc seconds. Okay, and the optics are a factor. Larger apertures produce smaller stars, and they also decrease the Dawes limit, which we are going to talk about in a moment. Okay, Dawes limit is essentially used to calculate the maximum resolving star of a telescope, or whether or not 2 close stars can be separated. Okay, this is always totally dependent upon aperture, with the 10-inch aperture having a resolution of 0.46 arc seconds and a 5-inch at 0.91. As the formula is very easy for this, but however, just note that it's proportional. Okay, if you half the aperture, you're going to essentially half the Dawes limit. So, and there's another formula also that I believe, it's the Raleigh criterion that's a little bit more exact than the Dawes limit formula, because the Raleigh criterion takes into consideration frequency also, where Dawes limit is just generally a ballpark idea. To tell you the truth, I think that anytime I go out, if I can't easily see all the stars in the handle of the Little Dipper, for instance, I figure it's not going to be a very good night for viewing. But however, that doesn't mean I won't go out. It just means it's not going to be a good night. Polar alignment, of course, it's always nice. Makes things a whole lot easy with a German equatorial mount or a fork mount. rough polar alignment usually fine for visual observing. You don't have to go through all the polar alignment that the astrophotographers do. And you can just steer to the target, and you're occasionally going to have to make adjustments, but it's not too bad. I did that, and as a matter of fact, with that, my first real telescope on a manual gem, which was a Sears Roebuck, was bought in probably the mid-1960s, and I just had a hand control that I track stars with. Okay, we'll get into some of the more interesting things. Binary stars. These are stars that are gravitationally bound. There may be many stars in a system, though, so they're not really binary. Binary would truly only be 2 stars. We have optical binaries. They are not gravitationally bound. They may be far apart, very far apart. And I don't really consider them to even be binaries. So, because we can look at anywhere in the sky, and you focus on a star, and you're going to see another star beside it. Visual binaries can be resolved with a telescope. We'll have a couple of examples of those. And spectroscopic binaries, they are resolved as a result of long-term study of the spectrum of the stars. I'm not sure exactly how that happens, but one of these days I'll figure it out. Okay, and eclipsing binaries, we're going to have a good example of that also, where the orbital plane will lie directly in line with the observer, such as with eclipsing binaries, it's almost like having a lunar or solar eclipse every several days. Okay, and here is Mizar and Alcor. Okay, that is the star in the bend of the Big Dipper handle. Is this, Dean, is this screen? Maybe I can move this thing, yeah. Okay, I like that better. That's the star in the bend of the Big Dipper handle, also called the horse and the rider, separated by around 2 light years, just as observed from Earth. And actually, Mizar A and B are spectroscopic binaries, and Alcor is also one. And this is actually some of my work where we have Mizar there and Alcor, and right here is Mizar and its companion, and Alcor. And these are all Class A, Harvard Class A stars. And as a matter of fact, these guys, all 3 of them are spectroscopic binaries, and Mizar's, both of those stars have companions that are Class A. And there's a Class M around Alcor, I believe. And you know, another thing I'll point out is that this was initially thought to be a pair, but then they thought, no, it's just an optical binary. But now what they're saying is that even although they're 2 light years apart, they are gravitationally bound. It's sort of a good example with gravity being the weakest of the 4 forces, but however, it may be the weakest, but it works across tremendous distances, such as in this case, 2 light years. Castor is another example where you get 6 stars for the price of 1, as was the case with Mizar and Alcor, about 51 light years away. A and B can normally be split with most amateur equipment. Castor A is 1.93 and B is 2.97, so that might be a nice target. And then there's a dimmer component, which is at 9.83. I have tried to photograph and tried to find Castor C, And as of right now, I have been unsuccessful, so I've never confirmed sighting it. So, and the next chart is going to be, I don't know how close of a representation this is, but however, this is the entire sextuplet system of Castor. Okay, we have whatever Castor C made up of 2 M-class dwarfs. We have Castor B with BA being it's a B class, and another red dwarf. Okay, and Castor A, which is I believe another class B and a dwarf, a red dwarf. So sort of interesting to see that many stars end up being multiple star systems, and it's not really hard to figure out why that happens, because they all are formed as a result of coalescing nebula. And yeah, depending upon how thick it is, you may get multiple stars in a single system. Okay, and the variable stars. Extrinsic, we're going to change in brightness as the result of being eclipsed by another star planet or rotation to a side with significant sunspot activity. Okay, I think that rotation to the side with significant sunspot activity might be out of the range of our equipment, but I don't know. I could look into that further. For instance, we have Algol, which most people are familiar with in Perseus, which eclipsed by a companion about every 2 days and 9 hours or something to the order of that. 2.9, that's not quite right, but however, I'm having a hard time translating 0.867 days, okay, into 24 hours. Okay, we have Beta Lyrae, which is eclipsed every 2.94 days. And if you're really patient, you could get Epsilon Auriga, which eclipses every 27.0 years, with the last one being in 2009. So you only have about 16 years to wait for that one. I will add, there's not a lot known about Epsilon Auriga. A lot of, when I looked into it, yeah, it was a very interesting star, just for the simple reason very little was known about it. And we have the intrinsic variables also, where the luminosity changes due to pulsations, eruptions, or swelling and shrinking. The most popular of them probably are the Cepheid variables, for historical reasons more so than anything. We have Mira variables with extreme changes in magnitude. And then there are lots of other intrinsics also. Okay, and we're going to go back here to messing around with this thing. Okay, Algol, also known as the demon star in Perseus. Okay, it is an extrinsic variable, probably the most popular one. It has a period of 2.867 days. When I first volunteered to do this presentation, I was really hoping to be able to get pictures with minima and maxima, but as a result of combination of factors, it's below the horizon right now. But however, between weather and wind and anything else that could possibly interfere, things just did not work out as well as I wanted it to. The maxima is right around brightest at 2.12, and the minima is dimmest at 3.39. And the eclipses will last about a little bit more than 9 hours and 40 minutes. Okay, the B and K stars actually within are separated by a mere 5.7 million miles. So as a result of that, the only thing that I know of that has ever separated them. There's the Shara interferometer at Mount Wilson. And there's a video in here that's you might want to take a look at too. I think the charts are going to be online eventually. Okay. And the minima for algo can be calculated at the Sky and Telescope website, and the link is included right here also. And we'll go a little bit further into the demon star. So, okay, we can see here that, okay, essentially this is the orbits, and from primary eclipse to another primary eclipse is 2.867,324 days. Okay, and what happens in the process of this? At the minima, this K star is eclipsing the B star, which is A right here. Okay, and as a result, you have the change in luminosity with just about a little bit more than 1 magnitude. And then you'll have just a very slight dip here with the secondary eclipse, because it blocks out the K star, which really comparatively to the B star is not very bright. And then you'll just keep on going through that cycle again and again and again. So actually, I had these charts first on binary stars, but I thought they fit into the variable stars a little bit better, because I talking about intrinsic and extrinsic. Okay, and you have Cepheid variables. These are intrinsic, which vary on their own, named after the original Delta Cephei. They have a strong relationship between the stable pulsation period and the luminosity. They tend to get bright very quickly, and then they get dim much more slowly. Brighter Cepheids have longer periods, and dimmer Cepheids have shorter periods. This luminosity can be used essentially as a yardstick to calculate distance, because if we know the period, we will know the luminosity of the Cepheid, and as a result of that, we can do some extrapolation. We can figure out the distance. This was first noticed by Henrietta Leavitt Swan in 1908. Henrietta Leavitt Swan is one of the great astronomers of the 20th century from my perspective. And this was used by Harlow Shapley to determine the size of the Milky Way, and also distances to such things as globular clusters. It's a little bit of an interesting story, and as a matter of fact, a little bit ironic story too, because Harlow Shapley was one of those who did not believe in the quote island universes, which is what we now call galaxies. Okay, but however, all Harlow Shapley would have had to do, he never tried to extend it over his findings and look at Cepheid variables such as in the Andromeda galaxies. And Edwin Hubble believed in island universes, so he pointed his telescopes at Cepheid variables in Andromeda and found that they were actually separate stars, and they were calculated at that point to at 1 million light years away, which we found out, I might add, is not correct. And they were again used by Hubble and Humason to establish Hubble's law of the expanding universe. And Humason worked very closely with Hubble, and he's sort of an interesting character because he originally started out as what they called a mule skinner on Mount Wilson. In other words, he just carted supplies up there. and eventually got to know some people, got to work at the observatories, and eventually worked with Edwin Hubble. And eventually also ended up with a doctorate degree, an honorary doctorate degree, although he only had an 8th grade education, which was pretty common that back in that area, back in that time frame anyway. But however, in the 1940s, Walter Baade classified that there was type 2 Cepheids, and they were older, not as luminous, with different periods than the classical Cepheids. As a result of that, they put other factors together, and it ended up, they found out that M31, the Andromeda Galaxy, was over 2 million light years away. So I'm not trying to take anything away from Hubble, because the big factor there was that we found out that all those spiral nebulas we were looking at were actually island universes made of billions of stars. Okay, and this is a chart depicting Delta Cephei. Okay, where, as we said previously, it tends to go up very quickly, and then it takes about twice as much time as it gets dimmer, back and forth with a very stable period. Well, and this is, okay, Delta Cephei is actually, it's not one of the stars of Cepheus, but however, it's near the corner of Cepheus. And it varies between 3.48 to 4.37 over little over 7 days. And for comparison, for instance, we have Zeta Cephei, which is at 335, and Epsilon Cephei at 4.2. What would be a nice science project, if you have a wide field scope, to get all three of these into the field of view and estimate the variability and the period. Okay, sometime we get enough clear skies to do anything to the order of that here around Denver, which hasn't been happening very often lately. So anyway, just a fun project. I think I might work on that a little bit myself within the next year, or when I get time. We have mirror type variables, long-term variables with periods of over 100 days, and normally less than 2 years. In the late stages of evolution, obviously red giants, named after Mir, okay, which is in the constellation Cetus. Mirror variables, they can change magnitude from anywhere in the range of 2.5 magnitudes to 11 visual magnitudes. The example Mira is changed from 2 to 10 over a period of 330 some days, or a factor of about 1600. Imagine living in a solar system that your sun varies that much. But however, that's not nearly so much as Chi Cygni, which varies between 3.3 and 14.2 over a period of over 400 days. And this is just some of the things that I find fascinating with stars. I can read about them and I can read about the physics behind them, but however, I certainly cannot relay knowledge as a result of that. So all kinds of other variable stars. Some of them are similar to Cepheids, but however, the periods, and they're not nearly so bright. So they're not good measuring sticks as far as looking at galaxies, for instance. Long period variables such as Betelgeuse, RV Tauri, Alpha Cygni, where Deneb is an example of that. And there are all kinds of variable stars where I find variable stars, I guess, some of the most interesting things in the night sky. We're getting pretty close to the end of the presentation, and I think I'm just about on time. I can cover these things very quickly. Round dwarfs, stellar wannabes had a little bit of, possibly a little bit of hydrogen fusion initially, but not too much. White dwarfs, neutron stars, one of my favorite subjects, even though I can't see any of them, but however, they're supergiant remnants with whatever a teaspoon of material, for instance, may weigh as much as Mount Everest. You know, just amazing, stripping the atoms down to nothing but neutrons. And we're not very sure at all what's happening inside them. Black holes, totally collapsed stars. Wolf-Rayet stars are sort of amazing. They're dying stars with temperatures anywhere between 20,000 and 210,000 K. Carbon stars, giant stars with more carbon in the atmosphere than oxygen. A good example of this is La Superba. And since it's a spectral class C, and I did try to image it spectrally, and it's weird, I can say that much. I'm still trying to figure it out. One of the latest stars that I took an interest in is one HD 222925, which was found in southern constellation Tucana. That has 42 elements found in the lower periodic table. This isn't unusual with some of the stars such as the sun even, but however, this is a very old star, so it was created very early in the universe, and we think that could have been neutron stars that collided or merged, and as a result of studying this star, we may find out more information about that. And amateurs can contribute significantly to stellar science, and they have in the past. Up until probably some of these orbiting observatories, there's so many stars in the sky, there's a good chance if you pick one out, you may well be the only one that's studying that star, which is a big advantage over the professionals who have only limited periods of time on very large equipment. We have no such constraint. We have observed variable stars, report the information to the American Association of Variable Star Observers. David Levy's book goes into a great deal of detail about that and how it's done. You can get into spectroscopy, photometry. I think that photometry, I don't know what's going to happen to it from an amateur perspective with the Hipparcos and the Gaius observatories making literally hundreds of thousands of measurements over hundreds of thousands of stars. So that's a question mark. We'll say the suggested reading and reference. If I had to pick anything specifically that would be good to, I would say for a beginner, The Secret Life of Stars by Lisa Harvey Smith. It's a very easy read and it goes into a lot of detail on just how fascinating these things are. Another one's Astrophysics is Easy, part of the Practical Astronomy series. Don't let the title fool you, but however, what's nice about this book, it includes a list of observable objects of any certain type from, all the different types of stars to galaxies and nebula, etc. Starlight is something that I have a copy of that, and anytime I go on any type of a trip to any dark site, I always carry it with me. As a matter of fact, I think on most of my trips, I always carry it with me. The day we found the universe, which is about essentially about Hubble and Humason and their discoveries of the island universes and the expanding universes. It's a great book, and as a matter of fact, I would recommend anything by Maria. A great author, and all of her books are easy to read and very interesting and very informative also. What stars are made of, is a book about a lady by the name of Cecilia Payne, who first discovered that stars are made out primarily of hydrogen, but believe it or not, in the 1920s, people thought that stars were made out of the same things in the same proportions as Earth. Unfortunately, what happened, similar to what happened to Jocelyn Bell and neutron stars, her boss ended up taking credit for this, which is always sort of a disappointment, because again, I think Cecilia Payne is one of the great astronomers of the 20th century. And a couple things in anthology of double stars. David Levy's Guide to Variable Stars is also very good. And I think that is going to end the presentation, which I am probably right around 50 minutes right now. Do we have any questions? I see we have some chats up here.
Yes, we certainly do. Thank you very much. That was very enlightening. Well, I put a couple of questions in, one of which you already answered, but my first question is, what are your goals when you're observing stars? Do you look for certain types of stars?
Essentially, that is exactly what I do. For instance, what you can do if you're going to look for certain types of stars, my favorites are variables, actually. So, but however, since I'm getting into spectrosity also, I am wanting to look at whatever, and I only have a grating, which is very low resolution spectroscope right now, grading lens, but however, yeah, I'll look for certain types of stars. You might want to look at stars such as, just for the fun of it, try and find Barnard's star or Wolf 359, which are red dwarfs. Okay, you might and try and get a picture of them. Watch, for instance, if you can set something up, watch Mir over a span of 300 days as it changes from magnitude whatever to up to 11, and record that. And am I answering your question?
Yes, yes,
Okay.
you certainly are.
Okay,
I
and
can understand if you looked at Mira quite a few number of days apart, you might not even recognize it as the same star.
what you have to do is look at the background.
Yes.
It's kind of sort of like, as my comment said earlier, if you look at Barnard's star, okay, and you take a reading, you take a picture of it right now, or even if you just would look at Barnard's star and you draw it. Okay, one of the reasons why I take some astrophotography is because I have no artistic talent. So as a result of that, I can take a picture of it, and then it might take 5 years, but however, you can see a change. And likewise with the Mira variable, or the one that's the Mira variable that's in, what is it, Epsilon Cygni. Yeah, you can, over 300 or 400 days, try and set on your clock a little reminder, to watch it or to take a picture of it, and how bright it is compared to some of the stars around it.
Mm-hmm. Mm-hmm. Yeah, I bet that would be very interesting.
Mm-hmm.
Greg Fogarty has a question. He says, is it possible to measure the distribution of star types in other galaxies, or is it limited to our own only?
For close galaxies such as Andromeda or M33 Triangulum, I think that it is indeed possible. And of course, all the galaxies that are going to be orbiting, the dwarf galaxies that are surrounding the Milky Way, the Large Magellanic Cloud, the Small Magellanic Cloud, etc. That is where a lot of the work was done with Cepheid variables. and trying to figure out their distance, and that's what established some of the baselines, and to say this is indeed a possibility of, we can use this to determine distances. And I would say, just because of the spectral type, if you have a large spectroscope and you have, which many professionals love, large spectroscopes, you could probably get a good idea, because right now we know that just about every galaxy that we know of probably has a big black hole in the middle of it. So we can do quite a bit, and then as galaxies get further and further away, and I don't know what that distance is, and I don't know how far the best equipment that we have, how far away a Cepheid variable can be, and we can still detect it. But, according to what's in the general neighborhood, the makeup is very much similar to our own galaxy.
I have a question. One of the questions that I receive actually from people who are not close to astronomy is, how do we know the distance to stars?
How do we know the distance to stars?
How do we answer that? What is a simple way to
parallax.
answer the question to the
Parallax,
distance?
you can. There are several methods. The most popular is parallax, which essentially involves a parallax second. Okay, that parallax second. This is something that I decided not to cover in this presentation, but a parallax second is essentially an angle, the angle with the short leg on it being 93 million miles, and then extending that 93 million miles out until until the angle at the other end is only a second. Okay, and what that ends up being is a parsec, which is equivalent to about 3.26 light years. Okay, I don't think I have any references on this computer to show you that right now, but that is the one way that you can do it. And what happens, you can look at this star and look at the parallax on opposite sides of the sun. And as a result of that, you can take the parallax angle, and the parallax angle was actually, let me think for a moment there. Parallax angle is equivalent to, or the distance is equivalent to the parallax angle over, 1 over the parallax angle. Okay, in other words, and that gives you the distance in parsecs. That method is only works up to, I think, something to the order of 300 light years, maybe not even that right now. So, but I would expect that with some of these observatories out there, such as the Hipparcos and Gaia satellites, they are capable of tracking down things down to very minute distances. And then also you can sometimes look at the Doppler, and about the only thing that can tell you, though, is whether something's moving towards you or away from you, but they can extrapolate information and use it somewhat as a measuring stick. Okay, but probably the most accurate way, and this is one of the reasons why there's so much variability in the information you see, such as on distance, plus or minus so much. And you can also measure the actual disk of the star and the luminosity of that and the star type, and put all that information together. It's a relatively complex process that I am just not prepared to discuss right now, but however, the big thing is parallax, and I can put a couple charts together and send them to you, Dr. Unsoy.
No, no, that's good enough. Thank you, Steve.
I'll tell you what.
Can you
I'll
stop
send-
sharing this? Stop sharing the screen so that we see other people if they have questions.
Stop sharing the screen.
Yes.
Okay.
Okay. Are there any other questions? Please raise your hand or come forward. I don't see any other questions.
Well, thanks. If I can thank everybody for being here,
Well,
I appreciate it.
Thank you, Steve, very much for an excellent presentation here. This is a very good introductory presentation for the stars. So we very much appreciate and thank you very much.
Yes.
Thank you. Thank
I
you.
think it was excellent too. Lots of detail. I'm going to go back and watch it again. I couldn't pick
Yes.
it all. You were not too fast, but I'm going to go back and watch it a few more times to pick it all up. That was a lot of good information.
Well, time very much crept up on me as I was watching the clock while doing the presentation.
Actually, can you forward the presentation to me at the PowerPoint as well?
Absolutely.
So
I will do
the library. Yeah.
I will do that immediately.
Okay.
What telescope do you observe stars with?
What telescope do I? Oh boy, it all depends on the situation. I might use a very wide angle, just an 80 millimeter refractor. I have a couple 10-inch telescopes also at 2 different focal lengths. Those are probably my 3 workhorses, but also I have a couple that, for instance, well, I guess the 5-inch scope I was using for the lunar eclipse the other week. So not so much for stars, lunar eclipse and planetary things.
I see. Okay.
So it all depends on the situation, but yeah, I think that just depend upon the situation. I'll do something different. And if I can make another suggestion to people, one of the things that I have found as far as double stars, if you can't separate them visually, if you put a Batonov mask on your scope, you will see a set of 2 spikes. So you know you have 2 stars there anyway. So if you don't have, if the Dawes limit is too high, in other words.
Oh, I see. Okay.
Well, we can stop the live streaming. Actually, this, Steve, this